Hello, and welcome to the acid-base theory and KW video. Let's begin with the Arrhenius theory. This theory states that acids produce hydronium ions when we dissolve them in water, and bases produce hydroxide ions when we dissolve them in water. Very, very simple theory. From there, we're going to expand over to the Bronsted-Lowry theory of acids and bases. This theory is a little bit broader than the previous theory. We're no longer required to be in water, but we can be in water. Now, this theory states that Bronsted-Lowry acids are going to be things that donate protons. And so a proton, an H plus ion, when that reacts with a water molecule, we're going to form hydronium. So it's important to note that we never actually have just free protons roaming around in water. They immediately grab hold of the water molecules to form hydroniums. And so in our example here, HCl is going to be a proton donor, water is going to be our proton acceptor. We're going to form hydronium as well as chloride ions. The Bronsted-Lowry theory states that bases are going to be anything that accepts protons. So it doesn't have to be hydroxide. Lots of other things accept protons as well. And so our ammonia is going to react with water to form ammonium as well as hydroxide ions. An important thing I should point out here is the fact that our water is actually able to act as either an acid or a base. Now, it's not a particularly good acid or base, but it can do either thing. In the previous reaction, it was a proton acceptor, and here it's a proton donor. I'd like you to now pause the video and please complete questions 1 through 4. Welcome back. Let's talk about the strength of acids and bases. Strong acids are going to completely ionize when we dissolve them in water. So one way to identify a strong acid is that we're going to have this one direction arrow in our reaction, meaning that every bit of our strong acid is going to react with the water to form hydronium as well as our anion here. Now there's only 6 strong acids: HCl, HBr, HI, HNO3, HClO4, H2SO4. These are the 6 strong acids that are common. And so any other acid you see, unless otherwise noted, you can pretty safely assume is weak, because almost all acids are weak. Moving on to our weak acid, right here we have a bicarbonate ion reacting with water to form hydronium as well as carbonate. And so notice one difference here is that we have the reversible reaction arrows. But if we didn't have those arrows, we could figure out this is a weak acid because it's not on our list of strong acids. This would probably be a good time to point out how to identify acids. Notice that acids have hydrogen at the start of the formula. So pretty much most compounds that begin with H and are not water are going to be considered acids. Now right here we are going to compare HCl, which is a strong acid, to acetic acid, which is the active component in vinegar. Now vinegar tastes delicious. There's a very small amount of hydronium ions giving it a tart flavor, which is why it's very yummy on French fries or salad dressings and things like that. So again, this is a weak acid, and only a small amount of our acetic acid molecules dissociate into hydroniums. Now if we compare that to HCl, we could take a look here and see that we have a whole lot of hydronium ions present in solution. And so this is a strong acid. It's going to be very, very acidic, and this would not be delicious on French fries and salad because it's so strongly acidic. It would burn our mouths and dissolve our teeth and all kinds of other bad things like that. Moving on to the strong bases, there's only a handful of strong bases. Essentially, the strong bases are going to be formed when we combine group 1A or group 2A metals with hydroxide ions. Other bases can generally be considered to be weak. And so here we have a list of several strong bases, but there's other ones that aren't on the list as well. One of the things that dictates whether an acid or a base is strong or weak is what's known as conjugates. And so if we take HF and we react it with water, we're going to form hydronium as well as fluoride ions. And if we look here, we can see these reversible reaction arrows clearly indicating this is a weak acid. Also, HF is not on our strong acid list. That's another clue right there. So in order to get back to where we started, in order for our reaction to go in reverse, the fluoride ion has to act as a base to accept a proton from the hydronium. That's how we reform the HF in the water. So in addition to having an acid and a base on the left side of the equation, we actually have a newly formed acid called the conjugate acid, in this case our hydronium ions on the right, and a newly formed base called the conjugate base which is our fluoride ions here, our new proton acceptor. So the conjugates will always be on the right side. Our our acid forms the conjugate base when it loses a proton. Our base forms the conjugate acid when it gains a proton. Our relationship here is the stronger the acid, the weaker the conjugate base. The weaker the acid, the stronger the conjugate base. Now let's go back for a moment and take a look at this. The reason for this is in order for our reaction to go in reverse, our fluoride has to be able to accept protons. The better proton acceptor this is, the more it's going to drive that reaction back towards the left side. So the stronger this conjugate base, the less able our acid is to donate protons. HCl, by comparison, is a strong acid, and HCl has a chloride ion as the conjugate base, and that tells us the chloride ion is a very crappy proton acceptor. It's not a very good base, because, again, the stronger the acid, the weaker the conjugate base. Now I'd like you to pause the video and please complete questions 5 and 6. Welcome back, everyone. Let's talk about the ionization of water. So water is actually able to react with itself in order to form hydronium ions and hydroxides. So one of our water molecules is actually going to act as an acid and as a proton donor, and the other water molecule is going to act as a base, a proton acceptor, and that's how the hydroniums and hydroxide form. That's what they're trying to show right here. So this proton is going to be lost to form this hydronium here when another water accepts it, and this water that lost the proton forms the hydroxide. And so this reaction is reversible, and I want to point out it only occurs to a small degree. So if we take a look at our equilibrium expression, so using our rules from the previous chapter, solids and liquids are omitted, so the only things that are included are our products. Kw, which W stands for water, is equal to the concentration of hydronium times the concentration of hydroxide. And this value is 1.0 times 10 to the negative 14th. In the previous chapter we mentioned the smaller this value, the more we favor the left side of the equation. So what this tells us is that at equilibrium we have only a tiny amount of hydronium and hydroxide in pure water. In pure water it's going to be 1.0 times 10 to the negative 7th of each. So pure water is going to be neutral, and it's actually pretty rare to encounter pure water. Usually it's going to have gases or minerals dissolved in it. But pure water will have equal concentrations of hydronium and hydroxide, and they'll both equal 1.0 times 10 to the negative 7th moles per liter. Now if we take our solution and we introduce an acid, a proton source, something that's going to create hydronium ions, what we see is our concentration of hydronium goes up, and our concentration of hydroxide goes down. So interestingly, we don't run out of hydroxide even in an acidic solution, but we do have less of it. The higher this concentration becomes, the lower that one becomes. Another way of thinking about it is the product of these two concentrations, the hydronium and hydroxide, has to equal that constant. So the bigger hydronium gets, the smaller hydroxide must be in order for them to still equal that constant. A basic solution is the opposite. We're going to have a source of hydroxide ions, so this concentration of hydroxide is going to go up, and our concentration of hydronium is going to go down. But even in a highly basic solution, we don't run out of hydronium, we just have less of it. As this gets bigger, this gets smaller. So what if you're asked to calculate the concentration of one of those ions? This is a typical problem. What is the concentration of hydronium if a solution of hydroxide has 5.0 times 10 to the negative 8 moles per liter of hydroxide? Well, essentially what we're going to do is use our trusty Kw equation. 1.0 times 10 to the negative 14th equals the product of these concentrations. We're going to work a little algebraic magic here and rearrange in order to solve for hydronium. And we're going to have our Kw here. We plug in that value, and then we're going to plug in our value from the problem right here. And we crunch our numbers. We come out with 2.0 times 10 to the negative 7th. Now I suggest you try this on your calculator, because sometimes getting it to do the right order of operations and multiply when you want to multiply and divide when you want it to divide, it can get confused with scientific notation. So it takes a little practice to get this to work. So give it a shot, see if you get the same value. And once you've done that, please pause the video and complete questions 7 through 11. Once you complete questions 7 through 11, I suggest you scoot on over to the discussion board and talk about your results with your classmates.